So I'm Eric Olsson. I'm a PhD student at Chalmers University of Technology. I did this work with Benjamin Eriksson, Adam Doupé, and Andrei Sabelfeld, with Adam being from ASU. So what I'm presenting here is SpiderSense gray box database-aware web scanning for stored XSS. So as alluded to in the keynote for this conference, stored XSS has remained elusive despite being one of these classic vulnerabilities. I'll use this example to sort of illustrate why current scanners have trouble finding stored XSS. So we have this sort of simple flow where a user can register via submitting some post to some server-side code, upon which some details about their post will be stored. So this username will be transformed to a nice name. This approved flag will be set to false in the database. And then after this information is into the database, only then can the admin user visit some management panel to approve this user's registration. And once the approved flag is set to true, then the admin, when visiting the site usage panel, will see that this user is logged in, but all the way over here, we'll see some unsafe reflection of this username payload in that the nice name is being executed. So when we try to explain roughly why black and white box approaches as they're currently specified don't really work so well for this problem, it's that they have trouble finding both source and sink flows and understanding their relationship. So for classic static analysis in the white box setting, then it'll have trouble accurately and efficiently modeling this database, which separates these two flows. And then for the black box approach, which is what I'm mostly focused on here, instead of being able to see this module or component level flow where this data is being transported server-side, then going through some server-side modifications in code, put in this database, and then coming back, and so on, what it will see from a black box perspective is just these sort of more abstract things where you want to input a username, register this user, solve this modification from username to nice name, and then approve the user. So after we've solved all these inputs and completed our source flow, then and only then can we solve our sink flow, where we retrieve this approved user, causing code execution. So if we try to generalize the problems I was explaining for this specific example, then we see that there's sort of 5 roadblocks for current XSS scanners, especially black box ones. So the first one is that any input in general needs to be solved. So for username, you need to be able to input a valid username. Then you also need to be able to submit this form. So you need to solve not just username, but all the inputs here. And then also challengingly from its black box perspective, we have to understand that this username is somehow being transformed in something else server-side. After this, then we might also have to solve some multi-step approach because we're not just registering a user via one request, we're also going to have to make sure that this admin sends a different request for approving. And after those 4 roadblocks are solved, then we get to this final roadblock where I identify that there's code execution on this admin site usage panel. So each of these roadblocks presents some problems, but especially in combination, we have a fundamentally hard problem. So the novel approach we take in this work is that we substantially relax the problem. So specifically, we're basically cutting in half. Instead of tracing all the way from input to output, so input being HTML or HTTP input to HTML context, then we're going to be in the database. So we'll put a payload directly in the database and check for its execution, which we were inspired by binary fuzzing. When looking at this example and the roadblocks more generally, most of them correspond to this input or source flow. So if we can do something else instead, then we are left with basically only the final roadblock where we need to identify code execution. And we have a good place to insert ourselves to replace this input flow because the database cleanly separates the source and sink in this vulnerability class. Of course, we do have some more problems because now we're shifting from this valid application inputs to possibly invalid application states, but I'll come back to that later. So to specifically say what we're adding when we say database aware, we're just adding this database access to the schema and data that the database contains. Otherwise, this typical black box scanner, which has access to front-end details, such as the client environment, the client-side code, and any network requests between itself and the server. Using this method, we'll discover unprotected outputs, so things in the database that are being reflected in an unprotected way, causing code execution. And we'll say that these represent code smells because either they are some sort of dormant XSS or they are already a full-fledged vulnerability. To dive a little more deeper into our method, though I won't go incredibly in detail here, you can refer to the paper, we do 5 steps which we break into sort of 3 modules within our scanner. So the first step is that we prepare our application by inserting some benign correlated data into the database so that we have something to modify with our approach. Then we choose our modification on a cell-by-cell level so we can accurately trace our impact, all the while avoiding sensitive rows which we automatically discover. So for example, if there's some SSL only flag, we don't want to switch that on or off during our scan. After having identified where we're going to modify, we will actually inject a payload, which is unique, so we can accurately track this. And we take into account some structured data. So if we have, for example, some serialized PHP object, we only want to affect the data inside of that, not the whole serialized string. At this point, we have to consider that we're not actually working with real user inputs. So we have to validate that we didn't break the whole web application by violating some implicit constraint on the data stored in this database. So we do some heuristics on this, specifically link content. After we've injected this payload and made sure that the application is still working, then we'll look for the payload execution using a traditional black box scanner, in this case, Black Widow. The result from this method is this sort of mapping of payload reflections, so the unprotected outputs from the database. So this is some results from a scan of CMS Made Simple. And the bottom left, you can see that in the admin bookmarks table, the title and URL columns can have payloads inserted such that it will lead to code execution on this admin panel for listing bookmarks. If you look at the code of CMS Made Simple on this list bookmarks page, you can see why these things are not being protected. According to some documentation, such as WordPress, outputs should be protected, so that's some small indication that we have some underlying fault. But I would say there's a larger code smell when we're considering this from a security perspective, which is the whole point of stopping XSS in the first place, because these things also are dormant vulnerabilities in that even if there isn't currently an input or you can't insert an attack payload into this database cell, this could easily be completed later, such as with a plugin. So in this result from WordPress, we can see that users, if you edit some display names, this will lead to code execution across the WordPress admin panel. Of course, you can't actually do this in base WordPress because you can't edit a display name once a user has been registered and it's also properly sanitized. However, with handy plugins for offering additional user management functionality, then in an old version of this, you actually do have a way to enter this unsanitized data. If you're still not convinced that these XSS or that these unprotected outputs are dangerous, then our empirical evaluation, where we link these to actual store access vulnerabilities with complete flow, might offer some evidence. So we do a typical setting of 8-hour scans coupled with 10 minutes of manual analysis, where we look at what inputs can actually flow towards these database cells or columns that we've identified in both reference and modern applications, and compare this to ground truth union of free-to-use store access detected by other scanners and cross-reference in CVEs. So we find a lot of new store access from this compared to all other scanners, in this case being Arachnid, Black Widow, and Zap. If we look into the exploitability of these reports and also why they result in vulnerability in general, the sort of input protections are varied and not so standardized. So some of them have no input, so this might be some base name or language field that never gets changed. But it might be validated, stripped, or escaped, but there's no real pattern to these. And we also, in the paper, you can look for our analysis of user models. So we're seeing if these things can actually be used to exploit, so to elevate your user privileges. To go back into these roadblocks, because this might offer some evidence as to why this approach is valuable in comparison to more standard scanners, we can look into a couple of applications. So on MyBB, we find 6 new XSS, which are only self-XSS, but still a vulnerability, which could be made more dangerous via something like CSRF. But anyways, none of our scanners can detect these XSS. But interestingly, other scanners could reach almost all of these inputs, so 4 out of the 6 of them. But why do they not detect an XSS? In this case, it's either due to them not being able to handle this sort of server-side input modification, or them not being able to complete to do a multi-step flow so that you can, for example, change this forum title after you have already made this new forum. As another example, we have CMS Made Simple, where you discover 8 new XSS. And in this case, the compared scanners simply do not reach the inputs. So we're able to avoid these general challenges of crawling and scanning by cutting the problem space in half. Yeah, so this is a summarization of our contributions. So we offer a novel gray box database-aware approach, which we implement as an open source prototype. And we do a practical evaluation wherein we systematize the relationship between unprotected outputs, stored XSS, and exploits. I'll say that these unprotected outputs represent codec smells in that they can be dormant XSS or vulnerabilities. And the gray box setting we're using here empowers defense, because the people that develop or run these applications are able to scan these in a way that an outsider is not. We have our artifact code and paper, FAQR code, and URL shown. Thank you.